Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to go through an example of an area calculation where we're going to end up with an integration by parts. So what we're going to do in this example is for the function y equals x cosine x, we're going to try to calculate the area bound between the x-axis and that curve on the interval pi over 2 to 3 pi over 2. So the first thing we're going to do is take a look at a picture. You know, the old saying, a picture is worth 1,000 words. Well, in math and physics, it's more like 2,000. And I'm going to just draw a quick sketch of this function, just a quick sketch. All right, so y against x, and we're looking on the region from pi over 2 to 3 pi over 2. So I'm just going to put pi over 2 right here and 3 pi over 2 over here somewhere. Now, x cosine x, the cosine function takes on a value of 0 at pi over 2. So I know this point goes through here. The cosine of 3 pi over 2 is also 0. And on the interval pi over 2 to 3 pi over 2, the cosine function is negative. So the graph in this region is probably looking, you know, maybe something like this. Exact shape not important. Right? What's important is this. I know that these are zeros, pi over 2, 3 pi over 2. There are no other zeros in this region. That's important because if there were, we may, in some cases, have to break the problem up into multiple integrals. But x is positive everywhere in that region. Pi over 2 and 3 pi over 2, there are no zeros of the cosine function in that region. The cosine function is negative in that region. So this graph looks something like this. It's continuous everywhere, it doesn't have any asymptotes or anything like that. Now, if we want to find the area, the first thing we need to do is draw in a differential element. So I'm going to do that. All right, so here's an element here, and I'm going to label this with a dx here. Now, the choice of labeling here, this depends on the type of method that you're intending to work the problem. If we're intending on working this problem maybe numerically with a computer and using, say, like n equals 10 points, probably label that as a delta x. The difference between delta x and dx is delta x is a finite measurable value. You can get a ruler out and measure a number for a delta x. Dx is an infinitely small thing. If we are intending to use an integral process, basically then the number of rectangles is infinite. The delta x becomes infinitely small, so dx would be an appropriate thing to label it as. Now, this length right here is equal to the function value, x cosine x. It's a negative number based on the graph, so I'm going to say this. All right, dA, which is going to be the area of this rectangle. It's all about this rectangle here. dA is going to equal minus x cosine x times dx. The minus sign is just taking into account the fact that this function's negative. If I multiply by a minus 1, this product is now positive. The length of the rectangle is the x cosine x, the width dx. Total area we would get by adding these all up. Or in the language of calculus, that's a summation, an infinite summation. And I'll go ahead and just bring that minus sign out in front, x cosine x dx. And then we're going to run this integral from pi over 2 to 3 pi over 2. So there's the setup. And again, if somebody forgot the minus sign, that'd be okay. What would happen is on this integral, they'd end up with a negative number for their area, but if they realized it at the end and went ahead and just took the absolute value, that'd be perfectly fine as well. All right, so we've set up our integral here for the area, length times width, and now we have to evaluate the integral. Now, when you evaluate integrals, again, there's lots of different integration techniques. You always have to kind of think about, you know, how to pick the techniques. And you'll notice it's the product of two functions here. X is an algebraic function. Cosine x is a trigonometric function. So that's the clue that integration by parts is going to be the preferred method here. Product of two functions that don't look alike. So when using integration by parts, I always use the acronym LI8. I'm going to go ahead and write it out. And this is for choosing the values, the function for u. And again, the L stands for logarithmic, the I inverse trig, A algebraic, T trigonometric, and E exponential. So you just go through the function you're looking at, and you look for the first one you see on this list to choose your U. So I look over here for a logarithmic function, and I don't see one. I look for an inverse trig function, and I do not see one. This is a trig function, not an inverse trig function. Okay. Algebraic function, yes, x is an algebraic function. So there's going to be my choice for U. So we're going to let U equal x. Whatever's left is your dv. So dv is going to equal cosine x dx. Now, I've got this minus sign sitting out in front, and I'm just going to leave that out in front of the integral here. When we're working the integral, show this in green, what we're working is this part right here. When we work this integral out. When we do this, we're going to get a negative number, and this minus sign will flip that back to positive. Right? After you choose your u, whatever's left is dv, then you calculate du, which would be dx, and v. Now the antiderivative of cosine x dx is sine x. So our integral, and I'm just going to write I for integral, is going to equal, right, by the integration of parts formula, it's going to be uv, that's going to be this product, x sine x, evaluated pi over 2 to 3 pi over 2, minus the integral of v du. I always remember this kind of geometrically. It's this product minus the integral of this product. So that's going to be integral pi over 2 to 3 pi over 2 of sine x dx. All right, so our integral is equal to, I'm going to go ahead and evaluate this now, 3 pi over 2 times the sine of 3 pi over 2. I'm going to go ahead, because I think I'm going to run out of room, and just evaluate. The sine of 3 pi over 2 is minus 1. Minus pi over 2 times the sine of pi over 2, which is 1. Running out of room, I got to kind of go down here for the rest of this. Minus the antiderivative of sine of dx is minus cosine x. Let me double check that. Derivative of cosine is sine, so the derivative of minus cosine, I'm sorry, derivative of cosine is minus sine, so the derivative of minus cosine is positive sine, so we're good here. And this is going to be evaluated pi over 2 to 3 pi over 2. So again, I know this is all one line below this. All right, so integral equals, I'm going to go back to this numerical thing here. So we got minus 3 pi over 2 minus another pi over 2 is minus 4 pi over 2. All right, and then this minus sign right here is this one, minus. Actually, as I follow this around, we got a pair of them here, minus and another minus. I'm going to go ahead and make that plus from this, minus, minus. Now, the cosine of 3 pi over 2 is 0, and the cosine of pi over 2 is also 0. So the integral is minus 2 pi. So our area that we're looking for, if I look back through our work, again, we were working the integral part, which is minus 2 pi, but our area here, we've got that minus sign in front of it to adjust, so the area there is 2 pi square units bound in this region. So about 6.28 square units. So Again, the purpose of this video is just to go through an area application problem involving integration by parts. I hope this video helps demonstrate these things. Have a great day.